Okay, so this is from 2012 AP exam question number 2. And this is a combination of probably conservation of energy and momentum in various different parts of the problem. So the situation we're given is a small and large sphere of mass m and 3m are stacked on top of one another and then dropped from some height. Okay, so the large sphere, of course, hits the ground first, it rebounds, and then they very quickly, the two spheres collide. So part A asks us for derive an expression for VB, the speed with which the large sphere strikes the floor. Now one tricky thing about this whole problem is we're never given any numbers other than that the two spheres are m and 3m. That's the only number we're given. So everything in this problem is done symbolically, which can make things easier. It can avoid actually calculation mistakes because you don't have to do any calculations, but you do have to do a good bit of algebra. Okay, so for the first part, derive an expression for VB, the speed with which the large sphere strikes the floor. That part we're only talking about the trip down. Now, since this is constant acceleration, it is gravity, you could use a kinematic equation for this. I am going to use conservation of energy, though. I'm going to say that the initial kinetic and initial potential is equal to the final kinetic and the final potential. If I call the ground 0, then that should be final potential. If I call the ground 0, that final potential is 0. And it tells us that they're dropped from rest, so the initial kinetic is 0. So what I end up with is mgh equals 1/2 mv squared. Right? Potential equals kinetic. Now the masses here will drop out. And when I solve this for VB, just rearranging some things, I get VB is a square root of 2gh. Now it's important here, particularly in a symbolic problem like this, to stay consistent and use the variables, the letters that they give you. For example, they call this H capital H, and that's important because later in the problem there's a different height that's lowercase h. So don't mess around with the things that they give you. Just use them the way they're given. Right? It's the easiest way to go. Okay, so for part B, okay, it tells us that a large sphere, this is indicating what's going on in the picture on the right. The large sphere rebounds with the same speed, excuse me, sorry, with the same speed VB. Okay, after it then collides with the small sphere, their new speeds are Vs for the small sphere, Vl for the large sphere. And now it wants us to derive an equation that relates all of these speeds. Well, this is a collision. Okay, this is a collision. So what we have to use here is, of course, conservation of momentum. So total. I'll use the summation symbol that they like. Has to equal total momentum final. Okay. Well, initially we have, okay, again, our initial situation is now this picture. Okay, our initial situation, I'll call up positive, is we have actually, I just glanced at the solution. They have down as positive for some reason, but there you go. Our initial is then mass, so m times VB, the small mass, minus 3m times VB. Right, moving at the same speed but in opposite directions. Afterwards, the small mass is presumably moving up at Vs. Let me see actually if they Yes, it does tell us the small sphere moves up and the large sphere has some speed VL. Now, because they don't specify what direction, this minus sign could go either way. It could be a negative sign or it could be simply a plus. So either way is fine there because they didn't specify. But there you go. That's your answer, right? This is sort of the nice thing about symbolic problems is you get to this equation and you're done, right? That is the equation that relates VB, VS, and VL that they ask for. That's it. Okay, and until they give us more information, we can't solve that. Okay. Fortunately, in part C, they give us more information. Okay, they say in this case, VL is 0. So imagine the large sphere stops after this collision. You use your equation from part B to determine VS in terms of VB. That means solve the equation for VS, but just understand that VB is still going to be in there. Okay. So, well, if I take the exact equation I wrote up there, m times VB minus 3m times VB equals minus m times VS minus 3m times VL, well, it tells me in this part that VL is 0. So I'm left with 3m VB equals minus m VS. Okay. Well, what do you know? We can cancel out all my m's, just divide everything by m. Okay, those all drop out. And I get VB minus 3VB equals minus VS. Just rearrange that to make it look a little prettier. VS equals 2VB. Okay, this side of course comes out to minus 2, PowerPoint, go away. Minus 2VB, but this is also minus VS. So when I simply rearrange that, I get this. Okay. So now the next part asks us to determine, is this collision elastic? And we have to justify our answers using all of this stuff we did in parts B and C. Well, hopefully you recall that the requirement for an elastic collision is what? Well, it's in an elastic collision, kinetic energy must be conserved. Okay, kinetic energy must be conserved. Okay, so what we have to do is see if we can figure out the kinetic energy before and the kinetic energy after, and see if they are the same. Okay, so before, the kinetic energy, of course we have to take into account both objects, the small and the large. Okay, so before I had for the small one, m VB squared plus 1/2 times the big mass, which was initially also at VB. Okay. Well, what we can do now is simply add those together. And when I sort of put all this together, what you're going to get is 2m VB squared. Right, so essentially we have VB squared here, m VB squared there, m VB squared there. 1/2 plus 3/2 is 2. Okay, so but that's as far as I can go. The after, plus large. Well, the small is 1/2 m VS squared plus 1/2 times 3m times VL squared. Those were the two velocities after the collision. Well, if you recall, VL was 0, so that goes away. And VS was what? It's 2VB squared. Okay. Well, guess what happens when I square the 2 and the VB, bring it out front and combine it, I get 2mVB squared again. Okay, so kinetic energy is conserved, and therefore the collision is elastic. Okay, collision is elastic. All right, now, next part, determine the height. Okay, so this small ball just doubled its speed, right? Doubled its velocity from VB to 2VB. Okay. And now it's going to ask us what height does it rise to above its original position. Okay. Now, a couple of things we can take into account. First, recall from part A that VB is square root of 2GH. So I'm just going to write that in the corner here so that we can use it when we want to, and we will want to use that. Okay. And this is a conservation of energy problem, right? I've got a ball that's going up at Vs. Okay. What is the max height? Okay. Well, I'll approach this again from a conservation of energy point of view. K initial plus U initial equals K final plus U final. I'm going to call this spot height equals 0 so that my initial potential energy is 0. Since we're talking about the max height, the final kinetic is 0. And I get 1/2 m Vs squared equals mg times whatever this h value is. Okay. Now, a couple of bits of substitution I can do. Okay, 1/2 m 2VB squared equals mg times h. Now recall, this is the same substitution I did up here in part D. Okay, so total kinetic energy is 2mVB squared equals mgh. Okay, and now this is where I get a bit stuck because I don't know what VB is. However, recall I have this expression from part A. This is where I'm going to use it. 2m times square root of 2g capital H squared was mg little h. And now we can start to simplify. 2m square root cancels with the squared. 2g capital H equals capital M g little h. Let's see, m cancels with m, g cancels with g, and we find that little h is 4 times capital H. We got 4 times the height out of this. Okay? Okay. Now, there are, everywhere I used conservation of energy, so part E, not part D, that has to be energy, but also part A, those could be done with kinematics. And if you look at the solutions on the AP website, they show you the energy version, and then in a second set they show you the kinematic version. Okay, so there are multiple ways to solve this. Whichever you are more comfortable with, whichever you see first, which like whatever one you think of first, is totally fine. You will end up with the same expressions. Okay? All right. Thanks, guys. Keep studying.